I'm Martin Weiss, and I'm going to be presenting to you a talk that I did at the Mila Medical Reading Group a couple days ago. Essentially, this talk is a big synthesis of a bunch of topics. The core of it is going to be about the syntax-directed variational autoencoder, which is a paper that came out in the last year. But more broadly speaking, we're going to be talking about methods of graph and structured data generation. Most of these papers are focused on drug discovery or molecular generation. But yeah, we're going to be covering kind of a broad range of topics. So here we've got neural networks, formal grammars, chemistry, and program synthesis. Neural networks and formal grammars are kind of the types of models that we're going to be mixing primarily in order to be able to generate this kind of structured data. And then the types of applications that we're going to be looking at are in chemistry and program synthesis. So first off, what's the problem space? So in drug discovery or molecular generation, there are many potentially pharmacologically active molecules. So this 10 to the 60 number is thrown around kind of a fair amount in this space. And so I thought I'd think about how did they come up with this number? Why is it so massive? And there's some rules of thumb, Lipinski's rules. And basically he said that there's these 4 rules, and any likely orally active drug is going to only break at most one of these rules. And the most interesting one that we're going to be talking about that dictates the space is the molecular mass being less than 500 Daltons. And essentially what that does to the problem space is it makes it such that you can only have about 30 atoms in your molecule. And then we have only a finite set of organic chemicals, organic atoms that we're going to be using to come up with these molecules. And then if you permute those possible atoms and you only have a max of 30, the set of potentially pharmacologically orally active drugs is about 10 to the 60, which is a massive number, and it essentially means that it's very difficult to generate and optimize in that space. So this is why we need models like this, so that we can identify potentially new life-saving drugs, or even just a new, better aspirin. How can we have an aspirin with even better properties? So this is the kind of space that we're going to be operating in. And this is an extremely hot field. So just in the past year at ICLR and ICML, there's been a ton of work in this direction. So the syntax-directed variational autoencoder, this is in the title, we're going to be talking about that a fair amount, was published at ICLR this year. We're going to be talking as well, just background about the GraphRNN from Will Hamilton and Leskovec. This is a super interesting paper as well that I highly recommend. And then the Junction tree variational autoencoder. This one kind of takes all of the records. I think it's currently state-of-the-art, but again, this field is moving extremely quickly, and there's just a ton of papers coming out. So by the time I post this, I'm going to be out of date if I'm not already out of date. And if I am already out of date, by all means, feel free to post in the comment section so that you can link people to the archive paper and link me to the archive paper so that I can learn more about this space, which I find extremely interesting. Yeah, and there's a couple other models that are more in line with the syntax-directed variational autoencoder. These two, this is the conditional VAE and the G-VAE, the grammar variational autoencoder, I'm going to talk about in the related work section. Yeah, so the structure for this talk is essentially I'm going to talk about background for a while, and then I'm going to talk about the related works, those references, plus a couple more things. Then I'm going to talk more about the SD-VAE with an example walkthrough of how does this model actually operate. That's where I'm going to actually try to get into the meat of how this kind of structured data generation happens. And the related works, I'm going to be a little bit more hand-wavy. And then we're going to talk about evaluations between all these models. Yeah, so here's some background. Some of these models use SMILES, which is a type of text format that lets us look at a string that represents a molecule. So here we have a molecule, just a diagram of a molecule. It's got some hydrogens on it. It's got some rings. The first step in constructing a SMILE is that we're going to remove the hydrogens. Those are going to be implicit. And then we're going to break these rings. There's a lot of ways that you can break these rings, but there's some rules that you have to follow. Essentially, you're going to be putting ring bond numbers here, indicating which atoms go together. So you can see here that there's like an N1 here, and there's probably another one somewhere later. Yeah, here's another one. So that basically is saying that there is a ring here that's got a couple nitrogens in it and some carbons, and that it's connected here, right? So that's what that string is saying. And so once we have this reduced diagram, simplified diagram, we're going to find the longest path. We're going to do a depth-first traversal of it, and that's going to be the backbone. And then what we're going to do is we're going to look at the things that are coming off of the backbone. So this is basically how we end up with our SMILE. So there are a lot of valid generic SMILEs. There's many text SMILEs that map to the same molecule. So here we have, I believe, ethanol. And there's many different ways that you can represent ethanol that is a valid SMILE. So here we have the hydrogen still. Here we have two different orderings. Here we have the bonds, the single bonds still represented. And these all are valid generic representations of the same molecule. And we're going to talk a little bit more about why that's such a pain in a minute. So you can convert that type of generic SMILE into a standard SMILE by applying a bunch of these rules. Here, they say that you want to normalize it by taking the organic subset as bare atomic symbols whenever possible. So you're going to remove these hydrogens and just have CC. So there's a bunch of these rules, like a lot of these rules. And at the end you get one of these, so a CCO. And there's another type of SMILE called a canonical SMILE, which is essentially just another way of saying it's a unique SMILE. And these are constructed via open source but kind of arbitrary algorithms. They're really useful. The Zinc database, which we're going to talk a fair amount about, and is a widely used benchmark of chemical signatures, uses unique canonical SMILEs. So the way that we get to a canonical SMILE, though, is basically via some kind of arbitrary algorithm. And what that means is that there's no universal canonical SMILE. People have tried to get there, but if you use different software or different libraries or different databases of SMILEs, you're going to end up with different canonical SMILEs, or you might end up with different canonical SMILEs. And the reason why you're doing that is basically because you're giving an arbitrary labeling to a molecular graph at some level. So it's an arbitrary labeling. So basically, this is kind of like the graph isomorphism problem, which we encounter in graph theory, and which is totally relevant to molecular generation. Essentially what it says is that if I arbitrarily label a set of nodes in my graph, determining whether a second graph that has another arbitrary labeling is isomorphic to the first is NP complete, or NP. We actually don't know, so this is just a fun little theory of computation side note. This book that was published in 1979, which is pretty famous, listed 12 problems and basically challenged people to come up with figuring out where they lie in terms of complexity theory. And all of them, except for 2, including the graph isomorphism problem, have been solved. So we still don't quite know where in the hierarchy graph isomorphism lies, but we do know that it is extremely difficult and computationally intractable for large graphs. Just how computationally intractable and can you map other problems onto it, we don't know, or we can't prove it at least. Yeah, and so these two graphs are actually isomorphic. Here's a mapping. You can check it in polynomial time. Look, I can start doing it. So if I take some function f and I apply it to A, this blue node, and I say, oh, it's 1. So, okay, so this blue node is connected to orange, red, and green. Orange, red, green. Oh yeah, those edges match. And then I go through this list and I do that for each node, and I can tell that it's actually the same graph that we're talking about. All of the nodes, it's the same number of nodes, and they're connected to by the same edges to the same nodes. So there's another angle on this graph isomorphism problem that's even more difficult, which is the graph edit distance. So if I take these two molecular graphs, I could make this into a graph relatively easily. It's just nodes with vectors that have attributes like the atom or the bond type on the edges. And then I ask, are these two, or what is the distance between these two graphs? It's actually an NP-complete problem to determine what the distance, like the minimum distance between these two graphs is. So basically it's like you'd have to delete this atom, and then you add an atom over here, and you add an edge right there, and then they're the same. So the distance is actually very small, but finding that is very difficult. And further, although it's extremely useful, so that as a training loss, that would be great, because you can tell this like visual inspection that these two molecules look very similar, and they probably behave very similarly. Again, I'm not a chemist, so I don't actually know if they behave similarly. But if you take the SMILE representation of both of these molecules and you compare them, it actually turns out that the edit distance between the two is 22. So we have these two almost identical molecules, and we have an edit distance which is 50%. And that kind of blows a hole in using string edit distance as your loss function, or contributing to your loss function, because this is these two SMILEs should be actually very similar. So you're going to have one heck of a model that can identify that these two very different SMILEs are actually corresponding to almost identical molecules. And so one of the very popular libraries that we use in order to get canonical SMILEs is RDKit. So you're going to hear chemists talking about RDKit a lot. So this is just a more visual demonstration of what I'm saying when I am talking about arbitrary node labelings. So here's an adjacency matrix for this little trivial graph. So this little graph has one node which is connected to 3 other nodes. Here we have the last row and column is connected to the other nodes. So this is the first node, second node, third node. But we could scramble these rows, and we could scramble this graph, and we wouldn't change any of the edges or the nodes, but we would make it look different. We would take the 4 and we would put it over here, and we would take the 1 and we put it over here, and we would rearrange these rows and columns, and it would still represent the same graph, but it's just another of the n factorial different permutations of that graph. N factorial permutations of the node labels on that graph. So when we're talking about graphs and we're talking about molecules, they're forms of structured data, right? So we can think about them as what rules do we need to apply in order to create this structured data? What rules would we break if we made an invalid SMILE, right? I showed you all of those various rules for normalizing, but here's a set of rules for actually generating a parse tree or parsing an input SMILE and determining if it's valid or not. So this is just a toy grammar. So if you look at the start node here, it basically it can generate an atom followed by a carbon followed by another atom. So this is a non-terminal token. This is another non-terminal token. This is a terminal token, basically meaning that you can't expand this anymore. This is a leaf in our parse tree, which we're going to talk about parse trees a lot. So for our first atom, we can expand it, and it can be either a carbon or a carbon with a ring bond. This is a ring bond. Essentially, it's just a bond with a digit indicating which other, where's the other bond that's split. Because basically when we're taking 2 carbons and we have a bond between them, we're going to be writing 2 single bonds or 2 bonds. And then a digit, which basically indicates that, those are actually the same bond, and that the 2 carbons or 2 atoms are bonded with each other. And these bond and digits just can be rolled out into terminals, which are either single bond, double bond, aromatic bond, or different digits indicating which ring it's a part of. And we actually have so that was an example of a context-free grammar, just as a type of formal grammar. And we actually have this massive context-free grammar which describes what valid smiles are. You can go and find this on opensmiles.org. But we're not going to talk too much about the actual CFG for open smiles because we're going to just stick with toy grammars throughout this talk. Yeah, so here's a more formal definition of a context-free grammar, just an example at least. I'm not going to get into the theory of computation stuff because that would be an entire separate class. Yeah, so a context-free grammar, here we have a language which the grammar defines. So we have, it can be A or AA or AAA. So this is the language that the automata will accept, the acceptable valid strings. But then we have a language which includes B. So you could give it a B and it will fail, but it's part of our language. You would never want to give it a B though because it would fail. So the regular expression here is just another way of saying what is the language of acceptable words. And then your context-free grammar just has one rule. It's basically you take a start token and then you can create a terminal, which is your A, or you can make an A and then another start token. I guess there should be a B. It could go to B or B and then start token, and that would actually define what this deterministic finite automata's grammar is that it's defining. Yeah, because you could give it a B and then it would go over to this fail state, and then whenever you give it an A or B, however many A's or B's, it will always not be in the language. And if you give it an A, then it'll be in the language. That's what's indicated by these two little rings here. And then if you keep giving it more A's, it'll still be in the language until you give it a B, in which case it's not in the language anymore. So this is a deterministic finite automata, which is part of like automata theory. There's many different kinds. So you could have a push-down automata, which is basically DFA with a stack, so it has some amount of memory. And then there are certain types of operations and languages that these automata can't actually accept. They can't recognize them. And one of the problems, which is present in the SMILES language, it's also present in Swiss German, interestingly enough, is the cross-serial dependency. And if you have a cross-serial dependency in a language, that means that it's a non-context-free language, which means that you can't create a push-down automata to accept it. And just, yeah, getting into complexity theory a little bit. Yeah, so in SMILES, we have these ring bonds. So C1 basically is saying there's a single bond to another carbon. So this is a carbon ring, essentially, is what we have right here, a benzene. And it's non-context free because we need to know that we're going to be opening and closing with the same digit here, this ring bond. And you can't write a formal grammar that will describe that relationship. Similarly, if you have an arbitrary number of cross-serial dependencies, as you might in a German sentence, instead of in English, we have helped Hans, so we know that we need to conjugate helped and Hans because they're right next to each other, and paint the house because they're right next to each other. What are you painting in the house? They're adjacent. So here we actually have serial dependencies. So the information that you need to know how to generate Asterix is present earlier and separated by some arbitrary distance in your sentence. Similarly, this number, is separated by some arbitrary distance from the other one in your ring bond, because you might have a ring bond that's separated over by many other ring bonds. So now I'm going to talk about two of the models that we're going to use. We're going to talk about recurrent neural networks and the variational autoencoder. So variational autoencoders were developed in 2014 by Kingma and Max Welling. And essentially what they do is they let us get a latent representation for a space of our data. So the idea essentially is that given some input data x, we're going to learn to encode that data into some smaller vector than the input data size. So we're going to compress that data into a latent vector z given the input data. And we're going to learn the parameters for our neural network that enables us to do that. And then we're going to take that latent representation of our data and we're going to be able to decode it back. So given that we have that latent representation, we're going to decode a piece of data, x, back out. And so x hat over here, or x tilde over here, is our reconstructed x. And we're going to have a loss on like how good is that reconstruction. So that would be our training loss. So just to give you like a more, hopefully a clearer example, if you give it an mnist digit, which is just a 7, here we have an image of a 7, which has like many binary values in an image. So we have a grid of many binary values. Is it a black pixel or a white pixel? And we're going to train an encoder on many of these images to have a latent representation, just a vector, which has maybe 100 latent variables in it, as opposed to the many hundreds of latent variables in the image, or many, they're not latent variables, just variables in the image. And we're going to learn what this latent representation is, and then we're going to be able to decode using another neural network. So given that vector, we're going to be able to get a 7 back out. That's the basic idea. And so we call this latent representation a bottleneck because it has lower dimensionality than our input data. That's the idea. So we're going to be able to find some compressed representation for our input data set. And then we're going to be able to, so we're going to be using our neural network to learn an encoding probability density for that data set, and then we're going to be able to decode from that latent representation back into, we're going to be able to sample from that density function a piece of data. And a recurrent neural network, which we're going to talk about and is used relatively widely as well in these kinds of models, essentially it takes in another piece of data, and usually recurrent neural networks operate on sequence data. So this x might actually have x at t0, x at t1, x at t2. And then we're going to give that into our neural network, and it's going to have a hidden representation here. And that hidden representation is going to be fed back in on itself, or at least part of it is going to be fed back, of that hidden representation is going to be fed back into itself at each time step. So at each point when we're adding x at t0, x at t1, we're going to add a new, the current hidden representation at that point. And we're going to output some piece of information, there's going to be some output at each of those time steps. So this would be like a sequence-to-sequence RNN. Okay, so I'm going to talk a little bit about some related work that has gone on in the field of graph generation. All of these papers are directed at the molecular graph generation problem, but most of them try to say that their methods could be used for other things, such as program synthesis or just general graph generation. So we're going to go through them briefly. They kind of fall into two camps. The first camp operates directly on the graph, and the second camp operates on the SMILE representation, which is just like a one-dimensional representation of a graph. So they're going to basically, we use SMILEs as a type of method for constructing a sequence out of a graph. And these other two are going to kind of use their own novel methods that aren't the SMILEs method, which is prevalent in chemistry. So the kind of model that we're going to need for these is pretty much the same, because all of these are trying to generate graphs in some representation or another. And to generate a graph, you have some n nodes, and you need to specify the connections between the nodes, either explicitly or implicitly in the form of the SMILE. And so basically that means that you have n squared output values to specify its structure, which is large. And then not to mention that these have non-unique representations, so if you give an arbitrary node ordering, then you get n factorial different equivalent representations for the same molecule. And as I mentioned, the graph edit distance is an NP-complete problem, so getting a loss from that is very difficult. And the approximation methods for doing that kind of operation are also pretty intractable. N to the 4 is pretty expensive when we're talking about doing machine learning. And for the first two methods, we're going to talk a little bit about the dependencies and the representation of the dependencies between edges. So the idea is basically that you're going to condition the generation of edges based off of the edges that have come before in the molecule. And even then, using message passing, this is a pretty expensive type of operation. So first we're going to talk about GraphRNNs. Just to give you the overview setup again, we have a space of graphs, and that's just like the arbitrary 10 to the 60 with n factorial representations for each one. And then we're going to sample s times from that space of graphs. This is our training set. So for the Zinc database, that would be 250,000 different graphs. Right? And then we're going to try to train a model to predict and understand the distribution of that, of P of G, of the actual underlying representation of all of the potentially valid orally active drugs. And yeah, so that's what we're trying to have our network, the distribution that we're trying to learn. I mentioned this very briefly earlier, but essentially when we're trying to take this set of graphs, this graph with a set of with an adjacency matrix, and we're trying to turn it into a sequence, there are n factorial different sequences that we can apply. So the probability that we're going to assume for the GraphRNN of any of those sequences is equivalent. So it could be 1 over n factorial. The probability of any sequence is 1 over n factorial. We're also going to define a function that maps from the graph to one of these specific node orderings, like an arbitrary node ordering, but that we're going to use consistently. And then we're going to define a sequence of adjacency matrices. Adjacency vectors. So this is like kind of the trick that they're using. This is the main contribution, I would say, of this paper, or one of them. Essentially what they're trying to do is to say, okay, so we're going to map this graph into a sequence, okay? So we're going to give it a node ordering, and then we're going to learn how to predict the next adjacency vector for a given node as we add new nodes. So like we start with no graph, and then we're going to add a node, and then we're going to keep adding nodes, and we're going to predict which nodes that new node is connected to. And so given some ordering at node n, so this is the last node, we're going to predict that this S is going to be the vector of other nodes. So it's going to have n minus 1 slots or values that are just a binary value that's saying, is it connected to a previous node or not? And that this whole set of adjacency vectors is going to define SPI. And they do a trick, which is basically they're going to collapse a bunch of those sequences, the potential sequences, down using like a breadth first tree traversal. So basically instead of having, well, you still have n factorial different arbitrary node labelings in the worst case with like a star graph. But in practice, this is going to help reduce the space of possible node orderings, right? So we had pi here, but now we've got a breadth first search applied to the graph with pi. And this is going to reduce the space a little bit and help out the model. Yeah, so as I mentioned, any node vector, any adjacency vector is going to be just a series of binary values with n different ones for n nodes. So each node has an adjacency vector, and the size of this adjacency vector grows. So essentially what that looks like is for the first node, we define S1 pi just to be empty. Like that's what we define it as. And then we add a node, and we're going to predict when we add another node whether or not that node is going to be connected to the first. So S2 pi, this adjacency vector, basically says the second node that we add is going to be connected to the first. And then we're going to add another node, 3. And this S3 pi, given the pi ordering, is going to be connected to the first node, but not the second node. Right? There's no edge here. And then the fourth node is going to be connected to nodes 3 and 2, but not to the first node. And we keep doing this. And basically, one of the clever things that they did was they deconstructed this model into 2 different RNNs. So there's one which is basically coming up with the next node to add. How many nodes do we have in this molecule? Because this is a general architecture. They can have, n can be an arbitrary amount of nodes, which is great because not all molecules that we're trying to generate are 30 atoms. And then we have another RNN, which is going to be doing the edge level updates. So it's going to be predicting which nodes are we connected to. And basically what they're trying to model with the neural networks, these RNNs, at least with the edge level RNN, is a product of conditional distributions. So we have the product of this adjacency vector at I, so the ith adjacency vector given this node ordering is going to be, so if we're trying to get the full probability of a given adjacency vector, a set of adjacency vectors, the probability is going to be each one given the ones that came before it. That's basically how you can think about the kind of distribution that we're going to be modeling with our neural network. And this is like really computationally difficult to model, but that's why we're going to be using neural networks to attempt to model it. And in practice, this works pretty well for certain things. They don't actually benchmark it given some of the normal kinds of benchmarks. They do more like distribution of graphs and less like validity of graph evaluation. But still, the types of graphs that it learns to make and the distribution is pretty impressive. Yeah, but basically where it fails is that they don't have a notion of structure generation. So at each point, we're just adding one node. And so if the, so if you're adding just one atom at each point, you're going to get structures that are semantically invalid. Yeah, so here we're seeing, this is a chemically valid, and then we're going to be adding nodes. And if we stopped at any one of these points, then we're going to have an invalid molecule, and this happens a lot. Yeah, so this is a big problem for this type of model. And the solution, which we're going to look at next with the junction tree variational autoencoder, is to do structure by structure generation. So the JT-VAE, the junction tree variational autoencoder, has a few steps in how this model works. The first thing that we're going to do is we're going to try to decompose this tree. So we have a vocabulary that we've learned from the training data. Essentially, we're going to be looking for bonds, like individual bonds, and we're going to be looking for simple cycles, and then we're going to cluster these cycles and bonds and collapse them into nodes in a junction tree. And the reason we're going to do this is we're going to try to remove all of the cycles from our graph. So once we've done this clustering, we end up with this junction tree, and each one of these was a chemically valid substructure or subgraph that we've collapsed and then figured out like where the adjacencies are. Yeah, so they have a few rules about how they're going to do this kind of decomposition. The first is that they're finding simple cycles and edges that are not in cycles, and then they're going to take two simple rings and they're going to merge them if and only if they have more than two overlapping atoms, because, and again, I'm not a chemist, because this is represents some kind of bridged compound, which is a specific kind of molecule. Yeah, and so then they're going to cluster all of these, and then if there was an intersection between the two, they're going to add an edge, right? So these are the edges that we see here. So now that they have this junction tree, they're going to encode it. And the way they're going to encode it is using a message passing neural network. Yeah, so if you don't know a lot about message passing neural networks, they're really great. They're kind of like graph convolutional neural networks, which are a kind of like a subset of the message passing algorithm. Essentially what we have is a vector at each node, and we have an edge vector. And yeah, and then we convolve, we like pass messages between all of these nodes, and then at the end we have some kind of MLP or affine layer, and then we're going to predict some vector, and that's going to be ZT right here, and that's our latent encoding of the junction tree. And so we're going to use that later to decode our junction tree and get our junction tree back. The other direction we're going to go is just straight from the molecule. We're going to represent it as a graph with each one of these nodes being an atom instead of a chemically valid substructure. And then we're going to do another message passing neural network with each atom being, with each node having information about which atom is it. They also have a bunch of other pieces of information that they put in to these feature vectors. Yeah, like the valence type, like the valence information. For the edges, they have like the bond type. But yeah, they do an embedding for all of these, so they have like larger vectors, and the model is going to learn how to do the embedding, given like some other information about the superstructure, and it's going to learn how to basically construct this graph latent vector that has more information about like what kinds of atoms and the more granular information, because we have the superstructure with the junction tree. And then we're going to take both of these vectors, and we're going to first decode the junction tree, and then we're going to decode, using the junction tree and our latent representation of the graph, our molecule. And the really nice thing about this is that because we have a vocabulary, what we end up actually doing is just trying to piece together valid substructures of the molecule. So we've decomposed it, we just map it, oh, this is like this kind of ring, right? And then we're just going to have to represent that kind of information in our latent vector, and we're going to pop back out that ring, so we can just map directly over a set of chemically valid substructures. And then we basically just have to figure out, oh, how do they go together? And we have a bunch of information about how they go together. Because we have these edges in the junction tree. There are different ways that these kinds of substructures can fit together. And that basically means that we're going to have some distribution and some uncertainty about what kinds of molecules we get back out. We're not just getting directly the same molecule back out, because you can take these substructures and fit them together in different ways, and we don't always encode that information perfectly into the bottleneck latent representation. But it works pretty much the best in practice. In terms of reconstruction loss, it beats the SD-VAE by like 0.5%. And in terms of constructing valid molecules, it is 100%, because it basically already is finding like chemically valid substructures and then just sticking those together. So now I'm going to talk about a couple other ways, other models. This one here is basically just the VAE that we saw before. So you're taking data and you're finding a latent representation of it, and then you're reconstructing. But we're going to jointly train it with another neural network, and we're going to try to predict molecular properties based off of this. And the idea is that if we are predicting molecular properties like certain kinds of affinity or drug-like properties, then we're going to find, and we add that loss in to our training loss, we're going to find a better latent representation. And it's going to be more like semantically valid and like have a smoother latent representation, so we can optimize it better and find better potential molecules. yeah, the problem with that model is that it's not actually connected to, so it's like an additional network that you have to train, which is a pain and takes more computation. The conditional variational autoencoder is kind of a riff on the jointly trained VAE. And essentially what they're going to do is they're going to take the information about the molecular properties here and the chemical structure here, and they're going to separate them, but then they're going to stick them together on this vector that they're going to input. So their training data, they give in the kinds of molecular properties that they're interested in, and they give in the chemical structure in terms of the SMILE that they're interested in. They're going to encode that into some latent representation where they still have the molecular properties stuck on the bottom of their latent representation. And this gives, basically it's nice because you only have two networks, an encoder network and a decoder network that you need. And it's also nice because you can kind of like hold firm, like you can maintain one piece of the structure, and then you can modify like the chemical properties that you want. So the idea would be like, here are the properties of aspirin. Like let's like hold that. So we can put that into our model and then say what kinds of structures that aren't aspirin are there that have aspirin-like properties. So you can ask this network, and it will be able to do the same kind of thing because you're getting a training loss on the latent representation for those properties in the same way that the jointly trained, kind of in the same way that the jointly trained VAE was. Taking that idea a step further, the grammar VAE tries to include the SMILES CFG, and we're going to talk a lot about trying to get a structured data result, because the CVAE, the conditional VAE, did not actually incorporate the type of structure formally into their model. So sometimes they're going to be outputting kind of gibberish, like invalid molecules. So this is a step in the direction, the grammar VAE is a step in the direction of having a formal grammar involved in the encoding and decoding process. So there's a few steps here, so we're going to walk through them. The first is on the left here, we've got SMILES grammar, which I showed to you earlier. And essentially, what we're going to do is we're going to take the input molecule, input SMILE here, and then we're going to parse it. And the CFG is this grammar is a set of rules that enables us to parse. So the SMILES goes to a chain, and then the chain goes to a chain and some branched atom, and then down to the bottom where you get some terminals here. And we're going to figure out which rules we needed to use. Okay, so this blue at the top is the initial rule. So this is a set of one-hot vectors. We're going to translate these rules into one-hot vectors. And then we're going to map those vectors into a latent space. Using a neural network. And for the decoding process, what we're going to do is we're going to map from that latent space into a set of probability distributions that are bucketed by the kinds of rules that we have in our grammar. Okay, so right here we see like different grammatical rules that we can use, that we can apply, and we're going to mask out some of the invalid rules. And then we're going to get a distribution over the possible rules that we can select, and then we're going to sample from that. So we're just using the types of rules that we know that SMILES and molecules, by extension, have to follow, and we're sampling those instead of. So it's kind of like sampling structures. This isn't exactly like a vocabulary of structures. It's a vocabulary of rules that we're going to be sampling and applying to construct a SMILE. We're going to go into more depth with the SD-VAE about how exactly this works, because the SD-VAE does it in a very similar way, and they have a bit better, in my opinion, visuals. So it's going to help us understand that a bit more clearly. And then they also add some other rules as well that help to create more semantically meaningful molecules. So now we're getting into the meat of the talk. I'm going to talk about the syntax-directed variational autoencoder, or SD-VAE. The SD-VAE is very similar to the grammar VAE and was definitely inspired by it. I kind of glossed over how it works because the SD-VAE, I like their visuals more, and I'm going to go into more depth. It also beat the grammar VAE in terms of a lot of the evaluation benchmarks, which I find interesting. So it also builds directly upon the syntactic rules that were included in the grammar VAE by adding an attribute grammar to enforce semantic rules. We're going to talk more in depth about what all of that means in a second, but first we're going to talk about what exactly is a semantic error. Here we have a little Python program. It defines a function called add5, which has an input variable of a, and then we have a commented line here that sets b equal to 5, so it defines b to be 5, and then it should return a plus b. Okay, so it takes the input variable a and it adds to it a undefined variable b here. And so when we call add5, what we expect to happen is for it to return 7, but it doesn't. It fails because it doesn't know what b is. The computer doesn't know what b is here because we failed to define it. So if we remove that commented line, this program should work, but it doesn't. And if we have context-free grammar or some other syntactic-only rule-based system, which is our compiler, this is a valid program to it. You can make a parse tree for it, but it is not semantically meaningful, meaning that a Turing machine cannot actually execute this program because it doesn't know what b is. So this is an undefined variable error. We're going to talk about this context-free grammar. That's just a toy grammar and a program here, which is syntactically valid for this grammar, but it is semantically incorrect because it has an undefined variable issue. So the first rule here is you can take a program, which is your start token, start symbol, and then you can have two statements that have a semicolon between them, indicating that the statements are separated. So we have two statements with a semicolon in between them. So we follow that rule. And then the second rule is that we have a statement which can be a variable equals a number, or a variable equals a variable plus a number. So on the left, we have a variable equals number, and then we follow the next rule for variable, and we get an a. It could have been any one of these. It could have validly selected z, could have still parsed it, but then, yeah. So over here we have a terminals, a equals 1, semicolon, is a valid statement. And then on the other side, on the right-hand side, we have a statement, and we're following the second rule. So variable equals variable plus number. So variable equals variable plus number. So we follow that rule correctly. Then we take the variable, we turn it into a b. So we select b here, equals, and then we turn this variable into a terminal, which we take c plus a number 2. And as you can see, the actual program, if you look just at the terminals, is a equals 1, b equals c plus 2. You might ask yourself, what is c? We don't know what c is. C is undefined here. So this program should fail, and a compiler that was just looking at the syntactics of the program, just looking at like, oh, did we apply these rules correctly? Can I parse this program? Yes, the CFG can parse this program, but it is not semantically meaningful. We have semantic errors in molecules as well. Here, we have a semantically meaningful molecule. So this is a valid molecule, but I'm just going to describe how you might break it. So this is a SMILE, right? And then we're in a Jupyter notebook, it looks like here. And then we have a library that's going to turn it into a molecule and demonstrate the molecule. So here, this one and this one indicates a ring bond. So essentially, the idea is that these two carbons are linked, but since we have a linear representation of this molecule, we actually need to put them far apart. Yeah, and so if you were to change and not have matching ring bonds, while your CFG would not be able to identify that that was a problem, it would be a problem for actually representing your molecule, because you wouldn't know where these ring bonds are matching, right? Where's the ring? You wouldn't know. So we can define semantic rules. So this is another toy grammar that defines a set of semantic rules that basically just says that we need to have matched ring bonds. So that's like the primary thing that's happening here. And we're going to go into more depth about how these semantic rules look, and we're going to have a parse tree with an attribute grammar that describes these. Just to trivially how you read this, it's pretty much the same as context-free grammar, except that the rules go differently. So instead of doing like a top-down parse tree, we're going to do a bottom-up understanding of the rule set. So here, just the exact same type of program that we did before. I mean, it's a little bit different because it's a molecule now, C-1. So ring bond, C-1, another ring bond. So just in the same way, we read it start token, and then we roll out, we parse, we create a parse tree for this molecule, and we check that the syntax was correct. And if it passes that, then we look at the semantics of it, and we start at the bottom, and then we build back up. So it's a bottom-up semantics check. So once we have this parse tree, we can look at the semantic value at the attribute. So this is an attribute on a terminal, right? We have attributes on non-terminal nodes as well. But here we have a value, which is the type of bond, and then the bond number, or ring bond number. And then over here we have the same one, and the set of those two is seen here, -1. And then are they matched? So if they intersect, if they're the same, essentially, then this is a semantically valid molecule that has matching ring bonds. Right? So that's what we see here, is a semantically valid molecule with matching ring bonds. This kind of grammar this kind of attribute grammar can have problems. Here we have another program, which is, I would argue, semantically incorrect. Some might say it's fine, but as a human, you would look at this and say, this program should add 5. And you give in your input variable a, and then you define b to equal 10, and it returns a plus b, which in this case, if you give it a 2 as your input variable, will return 12. So I was led to believe, by looking at the function declaration, that this function should return my input integer plus 5, but it returned it plus 10. So I would argue that that's a semantic error, but it's a really hard one to catch. What I'm trying to describe with this is that there are many kinds of semantic errors, and it's hard to enumerate all of them. So we looked now at 3 different models. Very briefly, I'm going to talk more about an example using the SD-VAE in a minute. But the idea is that the CVAE, the conditional variational autoencoder, where we were adding a 2-tiered vector as your input, part of it being the structure and part of it being the molecular properties, and then having a latent representation that had both of those things in your latent vector, just like including the molecular properties into your VAE latent representation, can output arbitrary strings. So it's not saying, it has no notion of valid structure, just in the same way that the GraphRNN has no notion of valid structures. It's just outputting arbitrary strings and hoping that they map to syntactically and semantically meaningful molecules. And you would check this with a library like RDKit, which has a big database of molecules and it has algorithms for checking a lot of these semantics, but it will fail to create valid molecules a lot of the time. The GVAE is a string yield of a CFG. Essentially, that means that they're making a parse tree in their decoder, and then they're reading off the resulting molecule based off of a syntactically valid rule set. So we have a context-free grammar for open smiles, or from open smiles, for smiles, and we're looking for we're creating generating a syntactically valid molecule. But the problem is that it's not necessarily semantically meaningful. Like, it might not have matched ring bonds, and that's actually really hard to enforce in a it's really hard to enforce or it's impossible to enforce in a context-free grammar. So now we're going to work on the SD-VAE, which has an attribute grammar, which can enforce things like that you must have matching ring bonds. And then you have the highest point, which is what we're hoping to have, which we have not yet successfully gotten to, although the junction tree variational autoencoder does an even better job by having its vocabulary of meaningful chemical substructures and then putting them together. Basically acceptable by Turing machine. So basically this means like that this program is acceptable by a Turing machine. So ideally that would be the kinds of programs that we can output from one of these models, and that it's outputting meaningful molecules, things that we could actually synthesize in a lab, or at least have valid matching link bonds. So there's two kinds of attributes in this attribute grammar that I'm going to talk about that we're going to use to describe semantic meaning. The first is an inherited attribute, which is computed from siblings and parents. So you're looking at those around you in your parse tree and those above you. And then synthesized attributes, which are computed from your children, from the things that are below you in the parse tree. And this is important, or the synthesized attributes are more tricky because when we're generating molecules, we just want to do one pass, ideally, because otherwise we're going to get into more computationally intensive situations. One way that we could do this kind of generation is we generate a molecule and then we have some checker, some library that checks all the semantics, like can we actually synthesize this? And then we throw away the ones that we can't. And that's what a lot of people have done. It's kind of like a Monte Carlo type randomization of identifying, oh yeah, these molecules are actually valid, and if you have 0.1% of valid molecules, you can still get a large set of valid molecules after checking them. The problem is that, one, you have to do 1,000 times more work with your model to generate these things, and two, it indicates that your model doesn't actually understand what it's creating. It doesn't have a good rule set. So now we're going to do an example of the SD-VAE. So up here we have just a little parse tree. So we're going to do just a toy example again using this parse tree. But it's going to get a little bit more complicated because we're going to add a stochastic lazy attribute. And the idea here is basically what we're trying to do. Again, this is for a decoder. Given some latent vector, we're going to try to describe a way to have a syntactically and semantically meaningful molecule be generated. And the way that we're going to do that is we're going to use these stochastic lazy attributes, and we're going to put them into our parse tree while we're generating top-down our parse tree. So the first step is the stochastic generation of an attribute. So when I say attribute here, I mean like the attribute grammar or semantically meaningful piece of information that's associated with a node. So here that's SA is your stochastic attribute. And basically this stochastic attribute is just going to be sampled from a Bernoulli distribution that is parameterized by a network. Okay, so this is where our neural network's coming in. Given that we have only a start token here, right? Start token and the tree at 0. So we have no tree yet, we just have the start token. And then we're going to basically have this SA either be 1 or 0. So this is a probability simplex. So the choices that we see here are either we could sample and then we could get a 1, and that we would set that as the value of the stochastic attribute, or we could get a 0. Yeah, so this is sampling to get an attribute. So this is an example of like the stochastic lazy attribute. And then over here, we're going to be sampling from the CFG's rule set. So here, there's only one rule. We could skip back to the CFG, but essentially what it just says is that when you have a start token, you turn it into an atom, followed by a carbon, followed by another atom. Okay, so there's only one rule that we can select given this start token and the tree. So we select it, and that's the start of our tree. So now we move down to atom 1, and since we randomly, using our Bernoulli distribution, not randomly, parameterized by our network, but we've selected SA, that attribute, to be 1. We pass that down to our first atom. So that's information that comes into our first atom that is going to be used to condition this sampling of our next rule. And essentially what that lets us do is that it says, instead of having this atom be able to be generated, be able to select one of two rules, with the first rule being there should be a carbon here, we X that out, we ban that option, and we only can take the second option. So this sampling, it can only sample from one option, so we just sample this option. And essentially that just gives us a carbon with a ring bond. And so that ring bond could be one of many things. So we're going to sample, given the tree at this point. We have no constraints. There's no semantic constraint on what kind of ring bond at this point, at least given the syntactic, the CFG syntactic grammar, and the semantic attribute grammar that we have so far. There are no, you could have any kind of bond, and you could have any kind of digit here. So we select one for each, and then we propagate these attributes back up the tree. So we selected a single bond, and we selected the value for that ring bond to be 1. And then the set of those two things is -1. And yeah, so this is just involved in the generation of our parse tree. Since we selected an attribute at the start, we now were able to pass that down and select the correct option for, select the correct option for the kind of molecule that we want to be generating. Or select, and we're going to see that being enforced in a second. So we don't actually have the full attribute yet for the root node. So here we have set -1, and we're trying to propagate that back up to the start node. And then the start node has two attributes that it's trying to enforce. Matched, where the intersection of the two branches of the molecule are matched with -1 at both, and that if that is true, if matched equals true, then OK is true. And since we now have this part of the parse tree rolled out, we have this attribute set is equal to -1, so we can push that back up and lazily evaluate part of matched. Okay. And since now we have part of matched, we can push that down to the other side of the parse tree. And so we're looking at atom 2 now, right? And so we're going to do constrained sampling given that we have this matched attribute. So because we have matched is -1, and we're enforcing matched ring bonds, we know that this branch can't be just a carbon, right? So we X out, we ban this option of just the carbon, and instead we expand a carbon with a ring bond. And we know that what kind of ring bond it is, so we can ban these two options in our probability simplex, and so we select the right type of ring bond. So once we have that matched ring bond, essentially we can just now propagate back up our matched -1 from this subtree to the start token, and that start token is going to have now the matched attributes. Matched equals the intersection of -1 and -1, which evaluates to true, and the OK equals true will evaluate to true. So this is how we try to merge our semantic attribute grammar with our syntactic context tree grammar. And then enforce the correct construction of certain semantic and syntactic constraints on our molecule. So here we were able to enforce the semantics of a matched ring bond on our molecule. So now we're going to do some direct comparisons of the models. We're going to see how they evaluate, which data sets they use, and the three primary ways that they evaluate these kinds of models are with reconstruction losses, the validity of the molecule, and whether or not they can do Bayesian optimization and predict molecular properties using the latent space that they've learned. There is another type of loss that is used primarily with the GraphRNN, which basically is looking at how the distribution of graphs that they've learned, how it matches up with the true distribution. We're not going to be talking too much about that here because I'm more trying to focus on the aspect of learning structured data. But it's still interesting nonetheless, and I highly recommend reading the GraphRNN paper. So the two types of data sets that they use primarily are the molecular and the program synthesis. So here we have a pretty widely used benchmark, the Zinc database. And so there's 250,000 SMILES in that database. And each one of these, or at least the SD-VAE, holds out 5,000 for testing. I'm basically going to be reporting the metrics from the SD-VAE paper, and then a little bit from the Junction tree variational autoencoder as well. The other type of evaluation that was done in this paper is on program synthesis. So there's 130,000 programs that they use, that they've synthetically generated, consisting of 1 to 5 valid statements, and they hold out 2,000 programs for testing. The way that these programs look is essentially you're inputting a variable zero, which takes on some numerical value arbitrarily, and then you're outputting, so you're returning some other variable from, and it's usually the last statement. So you define variable 8 here to equal the cosine of variable 9, which is defined previously on something that is defined previously, etc. And then you're hoping that your model that is managing this structured data generation can learn to validly construct programs like this based off of the latent space. So here we have the two types of data sets. We've got the program synthesis task and the Zinc SMILE task. Then we have reconstruction and validity. Reconstruction here essentially just means given some item in the test set, we encode it 10 times and then decode it 25 times, and we report the portion of decoded structures that are the same as the input ones. Okay, so it's how faithful a representation can we decode given some input data. And so as you can see, SD-VAE outperforms the other types of models on both of these tasks across the whole top line here. Most interestingly, I would say, is that they perform better in terms of the validity of the types of data that they can generate. Here they're always generating valid programs, which is awesome. They have like a well-defined semantics apparently for their programs. And then here they're still missing more than half of the semantics, I guess, or syntax, although I guess the syntax is probably pretty well defined. So basically what that means is that when they're decoding molecules, a large portion of them are not valid SMILE sequences. So from my understanding in the paper, they had a pretty limited semantic rule set, and that's probably, this is an artifact from that, I'm assuming, and that you could just keep adding more rules and keep pushing this number up. But that's not really a great strategy. I mean, ideally you could learn what the correct semantic rule set is, but that's a harder problem than program synthesis. So that's kind of intractable at this point. The reconstruction percentage is actually really good as well. We're going to talk a little bit. So this is basically the same table, except that the junction tree variational autoencoder beat all of the other methods. Again, this JT-VAE is kind of in a different track, I would say, than the ones that are operating directly on SMILES. Not to say that this isn't an extremely impressive result, it is. But I'm interested in like multiple forms of ways of managing structured data, and the one that they have is very impressive. So, but it's also interesting to note, while they have 100% validity, so they're always making chemically valid molecules, which is very impressive when you look at the comparison with the 43% that the SD-VAE is able to do. And this is coming from the fact that they have a vocabulary of chemical structures, and then just like being able to put these chemically valid things together, and it's learned how to put them all together in a chemically valid way, so they don't have to deal with like ring bond matching. It's like that's just part of the substructure of vocabulary that they have. And they said they had 780 different pieces of vocabulary, so they have like all these rings that they're using, and they're just popping them on, and basically putting them together like Legos, which is awesome. But in terms of reconstruction, it actually doesn't really do that much better. So, which is just an interesting artifact, I guess. Yeah, the way that you're putting these Legos together, there's still enough variability in that you're not always going to be getting the same molecule out given the same input. So there is still some, some interesting noise that's happening there. The other way that we want to evaluate these is to optimize for certain types of molecular properties, or in this case, we're trying to optimize our program to match some type of property. Here, the property is the output of the program. And then we're looking at the difference between the output of the program from our model and the output of the ground truth program. This ground truth program outputs this kind of sine wave looking thing. And then these other models are outputting kind of not as steep a sine wave. And we can see the kinds of programs that they were outputting. So the idea is basically for Bayesian optimization that you're looking at the latent space, you're generating a bunch of programs, you're seeing which ones have the properties that you're looking for, like they're closer to the ground truth, and then you take those, the representation of those programs, and you input that and you repeat. And so you kind of are trying to learn the kinds of input that you need, the kind of program that you need in order to have the described property. Yeah, and the SD-VAE outperforms here. It seems like it has a syntactically and somewhat semantically valid program that it's synthesizing. It's interesting to note that the GAV just totally fails. I guess it didn't have a rule for sine or exponentiation, which are both key pieces of this task. I don't actually know. I haven't looked into their grammar too deeply. So, but it's interesting to note that the SD-VAE does manage to get closer to this ground truth, but obviously it's still not quite there. And this is RMSE that they're reporting. So they're trying to describe how close was the output of that program to the ground truth program. And then they report the mean squared error as well for the sync task. And again, the junction tree variational autoencoder outperforms everybody else. So the latent representation that they've learned is apparently the smoothest, and it's the one that's best, you can use best for optimizing for certain molecular properties. Yeah, so they blow the SD-VAE out of the water. So again, very impressive with the junction tree variational autoencoder. And I just want to take a second to thank everyone in Mila Medical who suffered me through this talk, and everyone who is watching at home who is also suffering through this talk. If you have any corrections, please, I'm more than happy to go back and correct, update, modify, answer questions, anything. Yeah, thank you for your time.